Right, kicking on with some more forces questions. Looks like we've got a lot of moments happening in this one. Indeed, we're starting off with defining the moment of a force. So we need to have that the moment of a force about a point or axis, we need to have one or the other. But we say about a point is equal to the force multiplied by the perpendicular distance of the force from that point. Yeah, so we need all of those bits in there. You can't just, a moment doesn't just exist completely in isolation. It's a moment about a particular point or axis, and we need that perpendicular distance. So you need to include all of that in there. State the two conditions that apply when an object is in equilibrium. So we need the net force equal to 0 and the net moment to be equal to 0. So you have to put both of those things down. They're both net or resultant force. So resultant force, resultant moment, net force, net moment, whatever way you want to put it, but they both have to be equal to 0. Right, figure 4.1, we've got a human arm lifting an object. Lower arm is horizontal. Center of gravity is, it's marked that on that one, that 15 centimeters. Weight of the lower arm 18 newtons. That's on there. That's on there. That's on there. That's on there. So all the numbers are on there. Everything's on the picture. Define center of gravity. So center of gravity is the point where the weight appears to act. So the weight of an object appears to act. Yeah, simple enough. I mean, it's one of those ones you can work out, well, such as we might end up doing it in, well, we're not doing it in this question because it's given us the position, but you could in theory work it out through doing moments and things like that. Remember, the center of gravity is not necessarily in the same location as the center of mass, because if you're in a non-uniform gravitational field, then you're going to get variations there. Calculate the total clockwise moment about the elbow joint. So total clockwise, so we're going that way, we're going to have 18 multiplied by about the elbow joint. All right, okay, about here. So 18 multiplied by 0.15 plus 30 multiplied by 0.46. Right, so just type all of that in. Calculator's not coming on. Right, 18 times 0.15 plus 30 times 0.46 is 16.5 Newton meters. So don't forget your units. Easy enough. We multiply it forces by distances, so we're going to get all of that. That's completed part. Oh, C2. We've got C3 up here. As the lower arm is moved away from the body, the force F exerted by the biceps muscles acts at an angle theta, which they put on there. The lower arm remains horizontal in equilibrium. Describe and explain what happens to each of the following quantities as the angle theta is increased. The anti-clockwise moment about the elbow joint, that must stay constant at whatever it was, 16.5. I left the 0.5 off of there. Got it on my calculator, but I didn't write it in for some reason. 16.5 Newton meters. 16.5 Newton meters because in equilibrium. So there's no harm in putting that one in as well because at equilibrium. And the magnitude of the force F. So the as this angle is increasing, see what we want is F cos theta has to stay constant. So that equals a constant because D is a constant. So we need, as theta increases, cos theta decreases, so F must increase. So it's our usual chain that we have here of you have some kind of formula and we talk about how the variables in it are changing and it gives this, step one is that, therefore that, and then that's our answer, the usual chain stuff that we do. All right, we're first time for classic here, the old lift questions. They do like these. There are only two forces acting on the person. The weight of the person is 590, which they've given us, and then the reaction force is R. Show that the mass of the person is 60 kilograms. So that's going to be our 590 divided by g, which must come out as being 60, so I won't bother typing that in. The lift starts from rest. It has a constant upward acceleration of ½ meter per second squared. Calculate the magnitude of the contact force R. So we've got, in which case we've got R minus 590 equals 590 over g, i.e. the mass, multiplied by the acceleration, which is a half. So if we put all of that in, we're going to get 590 divided by 9.81 is that, multiplied by a half is that. I mean, I've gone back to the starters because I didn't know how close 60 was in the mass to being correct. I don't want to, end up getting double rounding in all of this. Plus 590, so we've got 620 and a little bit. So R is 620 newtons. After a short period of acceleration, the lift travels upward at a constant velocity. Explain why the force R is equal to the weight of the person if the lift travels at constant velocity. So we can, well, we're plugging it in really to F equals ma. So we're saying that R minus W equals m times 0. Therefore, R equals W. So you could do it that way, or you could just say, well, there's no acceleration. So if there's no acceleration, there's no net force. You've got different ways of putting it. So you could say V const imply, therefore A equals 0, therefore F equals 0, that sort of thing. Two different ways, whether you want to go the formula approach or writing out some sentences. Right, so state and explain how the force R changes at the instant the lift starts to decelerate. Right, so if we've got, deceleration, therefore W is greater than R, therefore R decreases. There we go. All right, this looks like it could be quite a quick one. There's not much on the face of it here, but we got write a word equation for kinetic energy. So kinetic energy is a half times mass times velocity squared. So not a lot really to say about that. It's just the 1 mark. They just wanted us to write out the formula with words in, which is a bit. Right, part B, a bullet of mass 3 times 10 to the minus 2 kilograms fired at a plastic sheet of thickness 1.5 centimeters. The bullet enters the plastic with a speed of 200 meters per second and then exits the other side at 50 meters per second. Calculate the loss of kinetic energy. Right, so we've got a half m. So our initial one is 200 squared, and then we've got to take off 50 squared. So yeah, we've got difference of 2 squares there. I suppose we could do 250 times 150. What was m? So we've got 1.5 times 10 to the minus 2 multiplied by 250 multiplied by 150. Well, we can get rid of that with those two. So we haven't got much left now. 1.5 times 25 times 15 is 562.5. We've only got 2. Let's go 560. So anyway, 500, and if I can write it out properly, 562.5, which equals 560 joules. Two significant figures, seems reasonable in this. The average frictional force exerted by the plastic on the bullet. So that is the work done. So that 562.5 is going to be equal to the average force multiplied by the distance. So we just need to divide this by 0.015, and we've got average force is 37500 newtons, so 38000 newtons to 2 significant figures. Right, so there we go. That was quite straightforward. Use your knowledge of physics to state if each statement is correct or incorrect. Do you need to then explain? Right, okay. They've given an example at the start. So in a vacuum, a 2 kilogram object will fall faster than a 1 kilogram object. So incorrect, because everything in the vacuum has the same acceleration. Fair enough. Right, mass of a particle remains constant as its speed approaches speed of light. Okay, we haven't actually covered this one yet. But it's incorrect because the mass increases with increasing speed. Mass goes up with increasing speed. So, but we'll get onto that in a later topic because we haven't got into any of our relativity or anything like that at the moment. All right, next part. A ball is thrown vertically upwards. The air resistance has negligible effect on its motion. During the flight, the total energy of the ball remains constant. Right, okay. Here I'm torn between what I think they're asking and what I think they're probably wanting, and maybe some subtleties on all of this. Because the thing that's making me hesitate is, well, potential energy is a property of a system, not a single object. So it's a little open to debate as to where the gravitational potential energy exists, but we don't really cover this. So they're probably going to say that's correct because we've got kinetic energy and gravitational potential energy are being transformed from one to the other. So we're getting these transfers between locations of energy. But you could probably go down the other route as well and say, well, no, because kinetic energy is a property of the ball and gravitational potential energy is property of system. It's the property of Earth plus ball. So you could get away with either answer on that one, I think. Right, C. An object falling through air has terminal velocity of 30 meters per second. At terminal velocity, the weight of the object is equal to the acceleration of free fall. Well, that's obviously incorrect because newtons is not the same as meters per second squared. So, yeah, we can just chuck that one straight out as being ridiculous. And then D, the technique of triangle of vectors is used by a global positioning system to locate the position of cars. Right, so we don't use triangulation, we use trilateration, as we've discussed before. So triangulation is looking at angles and trilateration is looking at distances, and that's what we use in GPS. It's distances to these different satellites rather than the angles to the different satellites. So we've got 3 of them are incorrect, possibly all 4 of them are incorrect. But we could do a yes, it's correct for the second one, depending on which description we want to give. And it's quite interesting in this because it comes back to this thing again. You know, so many people look at stuff in science where you've got, oh yeah, we've just got this definite answer. Yeah, this is 100% how we're going to put down the answer, and it's definitely correct or it's incorrect. But in this case, it's another one where it depends how we're describing the world. We can describe these things in slightly different ways using slightly different language, and it ends up producing these subtly different answers. Even though the same thing is going on, you know, we're still describing the same reality, but you can do it in slightly nuanced ways that are different. All right, now we've got another moments question. So, you know, repetition makes you more proficient on these things, even if they can seem pretty straightforward. Explain in terms of forces what is meant by a couple. So we need 2 equal and opposite forces. 2 equal and opposite forces, and they need to not be acting through the same point. Not acting through same point, or you can say that they're separated by distance, you know, something like that. But these are the key things. There's got to be 2 of them. They've got to be equal and opposite, and they've got to not act through the same point. Define the moment of a force. So the moment of a force is the force multiplied by, so, well, we need to say the moment of a force about a point is the force multiplied by the perpendicular distance from that point. So it's useful getting that in as always having the moment of a force about a point or axis. We could have either one of those. And then we have the perpendicular distance from that point or axis. All right, now they're giving us 3 forces acting on a rod. By taking moments about point X, show that the rod is not in equilibrium when acted upon by these forces. Okay, so we can look at clockwise and anti-clockwise and then see what's happening. So for clockwise, we've got 30 times 0.3, because, oh no, that's anti-clockwise, sorry. And that one's anti-clockwise, plus 10 times 0.2, and that's got to be equal our clockwise ones, if we were in equilibrium, of 20 times 0.6. So we've got 9 plus 2 equals 12, so it doesn't. So I've sort of done it if in equilibrium, then we've got that, so they're not in equilibrium. So we've got overall we've got a moment going clockwise, so there's a net moment in the clockwise direction of 1 Newton meter. That's the difference between the two of them. So yeah, there we go. You don't have to do this if equilibrium thing. You could just do a clockwise minus anti-clockwise, write it all out and say we've got 12 minus 9 minus 2 equals 1. So that's our resultant moment. It's the same sort of thing. Well, it's identically the same. So yeah, that finishes this little batch. I'll be back with more forces on the next video.